Okay, so in this video, we're going to focus on hyperparameter optimization, which is generally required if you're really wanting to try to get the best model performance that you can given the data that you've provided. Okay, so different algorithms are going to have different hyperparameters. This is just some examples. So some have more than others. For example, k nearest neighbors, generally just the k value, the number of neighbors. You can also optimize like which measure of distance you're using. One complexity with artificial neural networks are they tend to have a lot of different parameters that can be set. A lot of them are associated with the optimizer that's being used. And we already talked about some other parameters for different methods. So things like decision trees have like the pruning parameter, the depth, the number of features in a split before you stop splitting. Random forest has the mtry and the number of trees. Support vector machines is going to have the cost parameter, the slack parameter, and also kernel specific parameters like gamma, epsilon, or the polynomial order. So what parameters you may optimize is going to depend on the algorithm you're using. Okay, does it matter? Well, it kind of depends, right? That's one of the issues with hyperparameter optimization. You generally don't know ahead of time whether it's going to make drastic improvement. So if you really want to be sure, the only thing you can really do is test. So for example, in this is a paper by Hong et al. And here we're looking at the impact of the polynomial order. And generally, we're seeing improvements when we increase like the polynomial order in this case. So let's just look at this for A is with an equal sample size and B is with, so basically the number of variables and the sample sizes are varying. So you can see like it levels off a bit here. So in this case, it does seem like it matters a good bit. Over here, we're looking at changing the, let's see, what is this? This is the gamma for the RBF, radial basis function. And it looks like it's less important than maybe the polynomial order in the case of using that kernel. In short, it's going to depend. So if you really want to be sure, the only thing you can really do is test them and test some different parameters, as opposed to just using whatever the default settings are. Okay, so how do we actually do this? So generally to do this, we need to basically have different data partitions to train models and then to assess against. You generally don't want to assess performance on the training data because that can be biased. And there's a couple of different ways to create these partitions. Okay, so the first option is to just create a holdout set. So this is your standard where you have a data split of training samples and a holdout of testing or validation samples that you're comparing the model performance against. So effectively, you create the model using the training data and assess it using the test data. And then basically the best hyperparameters are going to be the ones that provide the best performance on the test data or generalize the best to the test data. Generally, this is maybe not preferred because it can be a bit biased, because if you test on some withheld test data and you get really good performance, that doesn't mean that those settings are going to be optimal for a whole other like new set of test data, like from a different extent or a different set of data points. So just doing standard accuracy assessment, holdout's a good way to go, but when we're trying to assess best hyperparameters, we tend to not use that method. Leave out cross-validation is another option. So this is pretty simple. Basically, the idea is that you train the model on all of the training data except for one sample, and then you predict back to that sample, and you repeat the process until every sample has been held out, and you assess basically overall how well it did at predicting all of those samples. So the best is going to be the one that provides the highest performance on the one data point that's held out. This is pretty slow, so I generally don't use this method, but it is an option. Okay, so the methods we tend to use are either k-fold cross-validation, repeated k-fold cross-validation, or the bootstrapping method. So first we're going to talk about k-fold cross-validation. So here's basically the idea. So we take the data and like training data, and we randomly split it up into k number of folds. So if we're doing 10-fold, it's 10 folds. If we're doing 5-fold, it's 5 folds, so on and so forth. It's common to use 10 or 5. 10 is probably the most common. But if you have a really small sample size, I tend to use a smaller number, so you don't have a small set in each fold. So what a fold is basically a non-overlapping set of the data. So imagine you have a bag of marbles with 100 marbles in it, and you want to create 10 folds. So you shake up the bag of marbles, pull out 10, that becomes a fold, pull out another 10, that becomes a fold, so on and so forth. So there's 100 sample points split up into 10 samples, and each data point is only in one of the samples or one of the folds. Okay, so then once you have the fold, so you basically go through and you train the model using k-1 folds, and you hold out one of the folds and you validate on the held out data. And you repeat that process k times. So basically if you have 10-fold cross-validation, each time you'll train on 9 folds and predict to 1 fold. And you'll repeat that 10 times such that every time a different fold is held out until you get through all the folds. And then you take those 10 iterations and you average out the results, and the one that provided the best average performance, the hyperparameters that provide the best average performance, is the best hyperparameters, right? So that's actually one of my preferred method or augmentations of it. So again, just really quickly, you have all your samples, you separate them into k non-overlapping partitions, then you train the model on k-1 of the partition, so hold out one of the folds, run it, validate it, run again with another fold held out, and you continue until all the folds have been held out, and then you average the results for each hyperparameter set, and the best performance is the hyperparameters that you choose. K-fold cross-validation repeats is the same thing. The only difference is that we repeat the folds a certain number of times. So you could, for example, do a 10-fold cross-validation, but do it 5 different times, and in each of those 5 different data sets, you're going to generate 5 new sets of folds, and then average things out. So the idea here is that you're just getting more iterations and more variability because you're going to use different set of folds or different data partitions in each of the repeats. So that can be a little bit more robust than just standard k-fold cross-validation, because again, you're using different set of folds, and you're using more iterations and averaging over more withheld data sets. Okay, and then the last option is bootstrapping. So basically how bootstrapping works is it's random sampling with replacement. So basically you'd say you're going to use 10 bootstrapping samples. So you have your samples like bag of marbles, shake them up, pull out 2/3, train on that, take the other 1/3, assess on that, then run it again, throw all your marbles back in, shake it up, pull out another 2/3, assess on 1/3. So how this is a little bit different from k-fold cross-validation is that each time you're getting a random set of training and testing sets based on random sampling with replacement. So we're not maintaining a set of folds that are non-overlapping throughout the entire process. Instead, we're just randomly pulling training and testing sets over each repeat. So it's a bit different from doing k-fold cross-validation. But again, you would do that X number of times and then average out the results, and the hyperparameters that gave you the best average results are generally will be your preferred hyperparameters. Okay, so how do you actually determine what hyperparameters to actually test? So there's different ways to do it. There's Bayesian techniques and stuff. I'm just going to explain the grid search method. Okay, so the idea here is that for each hyperparameter, you select a set of values to try. And then you have to actually go through and try each combination of the hyperparameters. So in this example, I have 2 hyperparameters. This hyperparameter has values A, B, C, and D, and this hyperparameter has values 1, 2, 3, 4, and 5. So we need to actually test each combination. So A in 1, B in 1, C in 1. So A in 2, B in 2, C in 2, so on and so forth. So effectively what it does is it goes through with like k-fold cross-validation or bootstrapping or whatever resampling method you're using. It grabs those hyperparameters, runs the models, runs it with all the the different folds and the holdouts, gets the average, then moves on to the next hyperparameter set. And then at the end, you're just going to take the combination that gave you the best results on average for the withheld data. So if you think about this, if you have a large number of values that you're trying and a large number of hyperparameters and you have to try all combinations, this is a lot of iterations of the model that's going to have to be trained and then assessed and over multiple folds or bootstrap samples or whatever. So unfortunately, the hyperparameter process using a grid search can be really slow. If you're testing a lot of values, you have a large data set, a lot of hyperparameters, whatever. This could take hours. I've had it take days before. If you are worried about how long this takes, you can look into doing like data parallelization methods. R has some techniques for that and some packages they can speed this up a bit. And there are alternatives to grid search that we're not going to talk about here. This is the only way to do it. So effectively, you're going to use a combination generally of some type of data resampling like k-fold cross-validation, bootstrapping, repeated k-fold cross-validation, and a grid search where you're effectively testing all these different models and finding the ones that give you the best model performance. So which of these methods should you choose? So things to consider is a number of training samples you have available. If your training samples are limited, it's not always easy to have like a holdout set. What algorithm you're tuning, how long it takes, the number of hyperparameters you have to test, the size of the grid that you're going to have to test over, number of values and combinations, all these things, and obviously computational time. Generally, I prefer to use k-fold, repeated k-fold, or bootstrapping. One thing to consider is if you don't have a large training set, for k-fold cross-validation, you probably don't want to have folds that have a really small number of samples in it because it could get noisy. So let's say you only have 40 samples and use 10-fold cross-validation. That means that each fold is only going to have 4 samples in it. So in that case, using a smaller number of folds might be preferable, like 5 folds, so you have 8 samples as opposed to 4. So those are just some things to consider. My de facto is k-fold cross-validation with 10 folds if I have enough samples. If I have a low number of samples, maybe 5 folds. The next question is what you actually need to optimize, and again, that's going to depend on the algorithm that you're testing or optimizing. So just here are a few examples for different algorithms. K is the KNN has the number of neighbors K. Decision tree, we have CP. Random forest is the number of trees, and the mtry, and then we have some options for SVM. Note there are other things you can assess too. So for example, random forest, you can have the smallest number of features for a split. So there's other variables that you can assess. Here is just like a few example ranges people test. It kind of depends. With KNN, like 1 to 20 is generally a decent range. For CP, a scale from 0 to 1 generally, so that's not too difficult. Boosted decision trees, generally you're going to eventually get to a point where it's not improving. So you might want to test from a low number up to a fairly high number, like 1,000 trees, and see where it starts to level off. Again, random forest, you don't need to optimize the number of trees parameter. If you set it high, then it's not going to overfit. But if you want to try to make it more computationally efficient, you can also just kind of test and see where the performance kind of stops increasing, so you can set a low number and not have a bunch of trees not really improving your performance. For the number of split variables, it's basically 1 through the number of variables you have, so that's a finite number of things to test. So sometimes I'll test all 1 through whatever, every single option. If I have a lot of predictor variables, I might do I might skip say do 1, 5, 10, 15, 20 as opposed to, all values. One thing that's kind of problematic with SVM is that there's a wide range of values you can test with these different parameters. The cost parameter, generally people look at 10 to the -2 up to 10 to the second. Here's an example for epsilon there. Polynomial order, could be like 1 up to like 10 or something. So SVM, there's a wide range of values. It's kind of infinite, so that makes it kind of a little more difficult than some of the tree-based methods to optimize. Okay, so how do we do optimization using the caret package? Again, I'll show you examples of this in the modules in R. But just as an introduction, the way we generally do this is we use the train control function to define some training controls that will go through the tuning process. So here I'm creating an object called train control, and using the train control function, I'm setting the method the CV, that's cross validation. Number is set to 10, so that means I'm doing 10-fold cross validation. And verbose iter equals true means it's going to print a bunch of stuff as it goes through and iterates, so you can kind of see how it's progressing. If you don't want to have a bunch of stuff printed to your console, you can set that to false. This is the different methods available. Bootstrapping is boot, cross-validation CV, repeated is repeated CV, LOOCV is leave one out cross-validation. The numbers argument for is the number of folds, so 5 would be 5-fold, 10 would be 10-fold. And then if you have repeats, the repeat option is the number of repeats. So 5 would be 5 repeats, right? So you create this train control object, and then when you actually train the model, you just call that, right? So here I'm training a KNN model. So here's my formula, the data I'm using, the method is KNN. This tune length parameter, I basically am telling it try 10 different values of K. It's just going to pick those itself. And then I'm giving it my train control, so it knows to use like 10-fold cross validation. And it's going to return the model. The best model is the one with the highest kappa statistic. This is a multi-class classification. Another option is if you want to actually give it specific values to try, instead of using tune length, you can use tune grid. So here I'm using this expand.grid, and I'm providing a bunch of K values using the combine function here. And then inside the model, I swap out tune length with tune grid, and I give it that grid. So in short, with the tune grid, you can give it an actual set of defined values to test. With tune length, you basically tell it to test X number of values, and it picks them itself. I generally just use tune length, and I get decent results, and I don't worry too much about it. But if I'm doing like research or I want to be very specific about what I'm testing, then I'll set up a tune grid and do it that way, because it's a little bit more easy to define and it's clear what's going on. Okay, what you can optimize on, like what metric, is going to depend on how you define the settings in the summary function and the train controls. Again, we'll look at this in the examples. So, for example, if you use multi-class summary, you can optimize on the overall accuracy or kappa. If you use two-class summary for binary classification problem, you can use sensitivity, specificity, or the AUC from the ROC curve. Here are a few other examples. So classification, multi-class, you can use kappa or accuracy. Probabilities, you could use ROC. Random forest has the out-of-bag sample, so for that algorithm specifically, you can optimize using the out-of-bag data. And then regression, you have RMSE or R squared. And again, that's just defined with this metric argument. So here, I'm using kappa. Okay, so whenever you do hyperparameter tuning and you're creating folds and whatnot, and this is also true when you're training any model that has a random or stochastic component, if you want to be able to get the same output every time, then you're going to want to set what's known as a random seed. So this in R is done using set.seed. A lot of people just use 42. It's the Hitchhiker's Guide to the Galaxy reference. So generally the rule in R is you can't just set a seed at the top of your code and assume that is going to be maintained throughout the code. Instead, you have to set a random seed right ahead of any line that has a random component. So like random sampling, training models, the cross-validation processes. So you'll see that in my examples. You'll see set.seed defined a lot because that's how R works. You can't just define it at the top and then have everything be reproducible throughout. So that's a common thing that you'll see in research because people want to create code and be able to run it over and over again and get the exact same output. And when you have things that have a random component like sampling or stochastic type learning methods like tree-based methods, you won't get the same result unless you set a random seed and you do it correctly. Okay, so I'm going to stop there. In the next section, we're going to talk about pre-processing and variable selection techniques. And then the last section, we're going to look at tidy models.